In this lecture, we continue the discussion of descriptive statistics for Stats 253. Here we're going to talk about the measures of central tendency and variance. In the Mendenhall textbook, this corresponds to sections 2.3 to 2.4 for central tendency and section 2.5 for variance, plus I've added some extra information on bell-shaped curves. There are three measures for central tendency, and that's mean, median, and mode. You've probably heard of these before in algebra classes, but what you might have missed, because I know the only requirement for this class is Math 107, and way at the end, the last chapter has some interesting things in it, such as this summation notation, and you might have missed that, so let's review it. Okay, the mean is the arithmetic average. Arithmetic average means add up all the numbers and divide by how many you've got. We're going to use whatever the variable is, like y. Some people use x, and that's fine too. Mendenhall uses y, so we're using y here. Y is the variable, is the value. Okay, when you have only the sample of the population, you can put y with a bar over it, meaning the average. The mean for the sample. For the entire population, use the Greek letter mu. It's pronounced mu. That's a Greek mu. At times, you will see these used interchangeably. Okay, but that's a distinction basically. They're both means. One is the mean for a sample in an experiment. The other is the mean for the entire population. Now, to calculate the mean, you add up all the values, divide by the number, and we use this notation. So the mean is going to equal the sum, and we use this big capital Greek sigma, that's a Greek sigma, to mean sum. And each one of the values we subscript with a little counter. That's what the y is, the I is, yi. And then you let the counter go from 1 to however many you have in, and you divide by n. So if I have, say I have three values, data values, 2, 6, and 5. Okay. Although it doesn't matter which one is first, I'll call this one my first one, so I call it my y value, but it's y1. This one will be y2, and this one will be y3. I just need to number them, but they're all y's. So I number them with a subscript. A subscript is not like a superscript in mathematics. It is just a counter, unless you get into things like Sobolev spaces, and then it gets more interesting, but we're not doing that today anyway. How many data values do I have? 3. So n is 3. Now when I write this formula, that would be y means equals the sum. I'll let I start at 1 and go to 3 of yi, because I know n, divided by 3. When I write this out, the sum sign means start at the lower end of the counter, I equals 1, and use that in place of the I. So that would be y1. Now let the counter increment. That means move it up by 1. So that would be i's becomes 2, and add it in. That's why you use this sign for sum. There's another one for multiplication, but we're going to use sum right now. That's what we want. So this is y2. Now you let the counter go to 3, and you add that value in, y3. And now you're at the top of the list, so you stop. You include the top number. Okay, so now we just have to put our values to it. 2 plus 6 plus 5 and plus 5, and divide by 3, and that will give us the mean. Okay. When you write this out in homework, it is very good practice to write everything, to write this formula. This does not have to be written. I'll put that in green. That's optional. That doesn't have to be written. And there's your answer right there on the outside, so that you learn that notation. Again, the big sign here is a capital Greek sigma. It stands for sum. This is the counter I. It's going to start at 1, and its maximum value is going to be n. The variable has a subscript I. That matches up. Let me get rid of, I got too much notation on there. Let me try it again. Okay, so I have y bar equals I equals 1 to n of y sub I over n. Okay, this is the counter. It also appears here. As the counter goes through its numbers, the different y values change, starting with 1 until I equals n, which is the maximum number. So here's an example. Let's say this is our data set. We have 13 data values. So because there's 13 data values, n is equal to 13. Fine. Now to find the mean, this is y bar, which you can't read very well because I put the font smaller. You're adding from I equals 1 to n of y sub I divided by n. N is 13, so you can see that's been replaced here by 13. Now you start with I equals 1. When I equals 1, here's my first data value, 25. When I equals 2, I pick up the second data value, which is 17. Keep adding them in until you get them all added up, divide by 13, and you get the mean. Sorry, that has that green bar around it. There, that's better. Okay, this is fine when you have a list of data points. Now when the data is grouped with frequency, you certainly don't want to add all those values by themselves. You can do it, you can find the mean using the frequency. So what we have in this example is we have the same summation from I equals 1 to n. We're dividing by n again. Everything's the same. We even have the yi's. But now we multiply by fi, which is the frequency associated with that y value. So let me write that out a little bit. So let's say n was 3. Then we would have the first frequency that's associated with the first y value. Multiply that together. In this case, this would be 3. Then you would have the second frequency times the second y value, plus the third frequency times the third y value, all divided by, it's not divided by 3 at all. Okay, it's divided by, and that's what's shown down here. Okay, an example is worth like 10,000 words, I think. Here are the y values. So this is I equals 1. This would be the second one. Whoops, I'm sorry. I equal 2. I equal 3. I equal 4. So now we're counting classes instead of the total number. How many data points do we have? We would add from I equals 1 to m being, in this case, the number of classes. So we're adding them up. 6 plus 3 plus 30 plus 1 plus 12. That gives me 52 data points. This means that there's 25 is repeated 6 times, 265 is repeated 30 times, etc. Okay, so now I know there's 52 data points. That's what goes in the denominator. Sorry, I can't move the graph. Okay, so now I know the total number of data points, so now I want to find the mean. So I take the frequency, here's the frequency, and I multiply it by the data value. And that's what I see here. 6 times 25. Now you might say, well, this is, pretty standard. And here's my 3, and I multiply it by the 19 because there's 3 19ths. I add all that up, multiply and add, I end up with them, and divide by 52, I end up with the mean for this data set. Okay, now again, I was going to say, you might say, well, this is pretty obvious, but it's not always obvious to everyone. And if you were someone who would have tried to add 265 30 times, don't feel bad. Other people have done it. So now just watch this formula and use the formula, and it will be easier. Also less error prone. The median is the middle value. If you have an odd number, it's easy. First, line them all up, and if there's an odd number, just pick the middle one. If there's an even number, average the 2 middle values. That's your median. Now that's pretty easy if you have a very small data set and you can line up the numbers. But if the data values are given with their frequency, it's just as easy. Only don't bother lining up the numbers because that's too much work and unnecessary. Okay, so here's some data values, and here are their frequencies. Okay, sort of put them in order. But total number of points is 52. The middle one is going to be 26. Well, it's even. You have an even number. I have to add the 26th and 27th data point. Where is it? Well, starting at the lowest, it's somewhere up in here. It's 265. It's in the middle. Well, there's two 265, so when I average them, I get 265. Okay? All you have to do is use the frequency. Do not write all the data values out in a big list. Count up to the middle. That was sort of an extreme example. For example, if that said instead, this was, say, 60. Okay, then how many points am I going to have? I've got 3 and 1's 4, I got 64, I've got 12, and I have 30. Oh, I wanted to come out even, but that's all right. 106, fine. So I have to divide by 2, 53. The 53rd data point, well, 53rd and 54th data point are in the middle because this has an even number. All right. So how would I find the 53rd data point? Well, I've got 3 here, 1 here. It's going to be somewhere in this group. So actually, it's going to just be 25. Sometimes you'll be averaging ones that are next to each other. But again, use the frequency. Don't line them up. Mode is the value that occurs most often. If there are no modes, that could be possible. If there's one, you call it unimodal, or if there's 2, bimodal. If there's more than 2, you can call it multimodal. That means 2 different values that occur the same number of times. And also the mode could be nowhere near the center. Now, an important point is that the median and the mode are not really sensitive to extreme values, but the mean is. So your average, your mean, is very sensitive to extreme values. So in this first example, remember we had, just for an example, we had 13 data values and the mean was 21.7. If you ended up, and say you added 2 more data values to this, so you had 91 twice, the mean changes to 35.7. If you take the 91 away, you end up with 15.9. So you get a change in the mean. Is this important? Yes, because sometimes in a data set you have what are called outliers. These are values that seem like they're a mistake. All the data is all clustered in one little area, and here are some numbers way out there, and they throw all your numbers off, and you'll want to take those numbers off and see what the effect is going to be. Sometimes you want to eliminate those numbers because they're wrong, but you will expect the mean to change when that happens. To understand a measure of variation, you first have to have the mean. So you have to know the average. And then you want to know, how is the data dispersed about that mean? Is it all clustered near the mean, or is it spread out? Those measures are variance and standard deviation. Range is just subtract the min from the max. Symbols for variance and standard deviation are the same. You use S squared for variance, S for standard deviation, because standard deviation is the square root of the variance. That's for a sample. For population, sigma is used. Okay, sigma squared for variance, sigma for this. What? Oh, I guess I had an error in this, didn't I? Okay, well, I'll fix it here. Okay, that error is also in the written lecture. I'll have to find that and fix it. Okay, what I fixed is that when you have the square on it, it's the variance. When it's not squared, it's a standard deviation. All right, recall that we had 2 different symbols when, for sample, mean, and population mean. The sample mean was y bar, the population mean was mu. And again, we're having 2 different symbols, one for sample and one for population. There's a relationship between them, or you can use a relationship between them, which we will discuss later in the course. The easiest way to get an understanding of what standard deviation means is to look at the classic bell-shaped curve. Here are 3 bell-shaped curves. They all have the same mean, which is 100, but the standard deviation, of course the variance, differs. Here's a standard deviation of 10. It's smaller than 30. You can see the red curve is clustered more about the mean with a smaller standard deviation. The ones with a larger standard deviation, the data spread out more. Here are the formulas for computing the variance and the standard deviation. Okay, for basically what you're doing, two equations are shown here, one for a sample and one for a population. But in general, let me just write out what it is. It's easier just to write it like this. Sigma squared equals, okay, you're going to divide by n, just like you did when you were finding the mean. And you're going to add again over all the data points from 1 to n, however many data points you have. You take your data value and you subtract off it your mean, either for population, or you can use y bar for the mean of a sample, and you square it. This is squared, okay? And then to get the standard deviation, you just take the square root of sigma. It's not really good form to try to write sigma equals the square root of all that, because basically you do the inside calculation, then take the square root. So you're adding from 1 to n, but you're taking each data point and you're subtracting how far it is. You're getting how far it is from the mean, and then you square that difference. Why do you square it? Well, if points are equally distributed about the mean, some are going to be above and some are going to be below. If you don't square it and you add it all up, you'll get 0. Let's go back and think again of the bell-shaped curve. The number of how the data values are clustered, how many % of them are in a certain area, is well known, although these values are approximate. If you look at the mean and you go one standard deviation to the left and one standard deviation to the right, so that's above and below the mean, 68% of the data approximately will lie, of the data values will lie in that range. If you go 2 standard deviations away, 95%. 3 standard deviations away, approximately 99.7%. Sometimes in business they'll talk about the 6 sigma and all that. You can see how far away 6 sigma would be. That would mean 6 standard deviations away from the average. So here's the bell-shaped curve with those values written in there. You have to pretty much memorize this. It doesn't matter. This doesn't matter. What I've done is moved, here's the mean right in the middle. This point, this green line, is the mean. I'll call it mu plus 1 sigma. Over here it's the mean minus 1 sigma. This point is the mean plus 2 sigma, and this point over here, the 60, is the mean minus 2 sigma. And the same out here, this is for the 3 and 3 sigma, minus 3 sigma and plus 3 sigma. Okay, if you go in this area between here and here, all the values between 80 and 120, 68% of the data values will lie there. If you go between 60 and the 140, you get 95%, and between 40 and 160, you get 99.7% of all the values. So this sort of template for the areas under this normal distribution applies to all bell-shaped curves. Let's apply this to the example given in the written lectures. Say you had sacks of potatoes that are delivered to you from 3 different farms. All right, they're supposed to weigh 100 pounds. Well, nothing comes in weighing exactly 100 pounds, but if you weighed them, did some statistics on them, and you found the standard deviation for each one, so you'd have to find the average, the mean, which we hope is 100 for all of them, and then you start measuring how far away each sack of potato actually is from that mean, square it, add all those up, square it, and divide by the number of potatoes that you, or sacks of potatoes that you were studying. Okay, for the hang and see in Bozeman, Montana, obviously I know that farm. Okay, actually it's a dairy farm, but that's okay. They have potatoes too. Now let's say the standard deviation was 10. Let's give 2 other hypothetical farms. Here's farm 3 with a standard deviation of 30. Think about that bell-shaped curve. This means that if I moved 1 standard deviation on either side of 100, 68% of the sacks of potatoes would be there. So that means 68% of the sacks of potatoes from the hang and see go between 90 and weigh between 90 and 110 pounds. For farm 3 with the standard deviation of 30, means 68% of the sacks of potatoes fall between 60 and 140. See, a much wider range. Now look the other way, and you can't do this from the graph I gave you. It has to be done a different way. But what percentage of the farm's sacks of potatoes weigh between 90 and 110 pounds. Well, let's set up for this top one. 68% lie between 90 and 110 for the one with a standard deviation of 10. But down here, only 4% are in that range of 90 to 110 pounds. So this is the kind of mileage you can get off of mean, standard deviation, and a bell-shaped curve, normal distribution. If the curve isn't exactly bell-shaped or you aren't really sure about it, you can still use the mean and standard deviation and Chubyshev's theorem to compute it, at least if you're greater than 1 standard deviation away from the mean. The formula is 1 minus k squared, where k is a number of standard deviations. Here's an example. Let's say you had data on the time to fail in hours for samples of Kevlar epoxy used in the space shuttle. So it looks like here we've gotten 12, well, we have 13, what? Well, we've got 12 samples. I divided by 12. The n minus 1, that's kind of fudgy. Okay, so what is the mean? I add up all the values and I divide by 12. Forget the n minus 1 right now. I'll just divide by n. Sometimes for a sample you divide by n minus 1 instead of dividing by n. But I just divided by n even though I wrote the other formula. So I'll only get partial credit for that. I would probably take off 1/4 of a point for doing this, or maybe an 1/8 on your homework. So now from the other page, I found that the mean was 1.201. Okay, I want to find the standard deviation. So first, I usually set the work up in some kind of organized fashion, and this is so important. If you're going to do this sideways and on the margin of a piece of paper, forget it. You're not going to get it right. Line up your data values in a chart, just like that. They're right there. Then you take the value minus the mean. Here it is. So that first column was the value, 0.080 minus 1.201, and that's what I write here. Then I square it. Okay, that gives you a nice organization. You can find the errors, otherwise you really can't do this kind of work. It can't be done sloppily. Okay, I need to add up all those, so I add up this column and I get 7.847. That will go in the numerator of the equation for variance and standard deviation. So now I go to compute the variance and the standard deviation. The variance s squared, it has that sum which I computed in the table on the previous page, 7.847. In this case I divided by n minus 1 and I got the variance. For the standard deviation, you take the square root of that.